center of mass for a non-uniform object. Now, I just gave you a one-dimensional object. Okay, two-dimensional object or a curved object or something gets substantially more complicated, but not substantially. It's just a little more complicated. Okay, you can figure out the center of mass for all sorts of shapes. In your book, they've got some good derivations for some of these, if I remember correctly. But here is our non-uniform object. All right, if you think you got it right, you can turn it in. If you're pretty sure you didn't get it right, you don't have to turn it in. But if you want to turn it in, you got to turn it in now. Anyone? 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 No. Okay, in this case, we have a bar of length, I don't know, what did I say, L? Is that right? And it has a linear mass density of, what was it, AX. Okay? So it changes. So at x equals 0, it has a mass of 0, a density of 0. And over here, at x equals L, it has a density of AL. Okay? So it gets substantially heavier as you go down from one side, from left to right. Now, the deal is that you could visualize this if you wanted to be an object that was maybe more like this. Okay? So the object has very little density on this side, or it's thinner on this side and thicker on that side. Okay? It would be essentially the exact same problem if you had a triangular shape like this. Okay? But we have an object that is shaped so it has a different density as it goes through. Okay? All right, so our equation for center of mass. Center of mass in this x direction. Okay? What is that? We got a couple integrals. What are they? RDM. Or for us, it's going to be XDM, right? Since we have x dimension. And what's on the bottom? DM. Okay? All right, so somehow we have to integrate that in here. All right, so how do we do that? Okay, lambda equals m over L, dm over df. All right, and for us, that's x. Very good. All right, so what do I do with that? Solve for dm. And what does that give us? Lambda dx. Substitute that in right here. Integral x lambda dx. Do we do that down here as well?
Yes.
Okay. And so we get lambda dx here as well. All right, what do I do next? Okay. The very first thing we've done is we've connected these two together, right? Connected those two by this idea of density. Okay? Because as you move through x, you're moving through mass, so you have to connect those two ideas together. So we've done that. And then we get this, so now they're connected, but now we have to know what lambda is. So we plug lambda in. So we plug lambda in here and here, right? So we get integral x ax dx, or we can rewrite that prettier. We get an a on the outside, x squared dx, right? And down below, we just get ax, right? A integral x dx. Okay, once we get it to there, we can solve that, right? Okay, so what's this become?
1/3 x cubed over 1/2 x squared.
1/3 x cubed over 1/2 x squared. X's go by. And our a's go by over here, right?
Yeah.
All right, so we end up with 2/3 x. Ah, yes. We do need some limits, right? Technically, we should have written those up here. 0 to L, 0 to L. And so technically, this should have already been changed, right?
Yes.
It should have been L to the third and L squared, giving us just 2/3 L. And there you go. All right? Very nice. Like I was going to do an object. like this, where the object is shaped like this, and here's our object. It's like a triangle, essentially, right? And you're going to find the center mass in this direction. And it turns out, because, see, essentially, this is the same as a linear change in density, okay? And for every triangle, if you go from the point outward this way, in this direction, this will be 2/3 of the side, okay? And then if you go down this way, it will also be 2/3 of the y direction this side, okay? So it'll always be in that spot,
So
as long as it has a linear transition.
Test, can we just automatically jump to that conclusion?
Yes. Now, I doubt seriously if they would give you one, a two-dimensional object like this. If they give you one on the test, obviously it's either going to be a conceptual problem like a multiple choice, so that you could, you know, if they have something like this, they'd say, well, where is the center of mass? You know, and they put like the spot here, spot here, spot here, and you know, you could figure it out. They'd probably put one here, 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 and here, and then where is it closer to? Well, it's obviously going to be closer to this side right there, the heavier side, right? If they give you one on the test where you have to find the center of mass, it's either going to be a lumpy mass object, which is much simpler than this, because you just add up the different parts. Or it's probably going to be a one-dimensional object, just because of a lack of time on the test. That would be too much. In fact, I would suggest for most of you that you would skip it and come back to that part. Just because. Now, what they may do sometimes is they may say, okay, the center mass is going to be at 2/3 L, measured from the left-hand side. And then they'll say, what equation would you use? Or set up the integral that would be used to find that. And so you would set it up, you know, get it to this point right here probably, which is not a whole lot more work just to finish it in this case. But they might give you a function that's a little bit more complicated. And it's the same idea. Okay, you have to use density to relate your location and your mass. And then if they give you a function for the density, then you use that and plug that in. Okay, and by the way, everybody, that's going to be the same thing that we use over and over again when we get to static electricity. So if you didn't understand this, you need to get an idea of how this works. Because we're going to be doing this when we get to charge densities. Because charges do not necessarily all lay in one spot. Like for instance, when we have a sphere, the charges may not all be on the outside edge. Okay? What they may give us is a charge density. So the density might be something like, you know, A times R. Okay? And essentially it's a very similar problem to what we did here, except we're integrating out radially. Okay? So we have to find out the total amount of charge and like the electric field or the electric potential. Okay? So we will see this kind of thing again and again and again. In the second 6 weeks, we'll see this again and again.
No. The grade.
What's that?
The grade goes on the second.
What grade?
No.
I've already put those in. Yeah.
Over DL lambda, but DL.
I have the power and I sent them in.
You have
DM over DX.
8 hours, 7 hours.
I sent them in 30 hours in
So
advance.
like,
All right, now.
you used to take pictures
December 1st is way too close.
15 days.
Okay, let's talk about not yet. We haven't even done regular yet, hardly.
For me,
Okay, conservation of momentum. Now you remember, the sum of the forces equals ma.
Yes.
Okay? But A is really dv dt. So if we plug that in, we get the sum of the forces equals m dv dt. All right. if we assume that mass can change, which it could in the most general sense, mass could be changing as things go on. Like when you drive a car from home to school, the mass of the car changes.
Gases.
Yeah, because the gasoline's getting burned up. Like right now, your mass is changing. You have a small mass change with time. Because if you sat there, you lose weight. Because your body is keeping yourself warm. You're a warm-blooded animal, which means that your body expends tremendous amount of energy just to keep you warm. So you're burning fuel all the time. That's why we have to eat so much. If we were a reptile, we could eat once a week. It'd be no big deal. Of course, on a day like today, you'd have a hard time. That's the way you eat. Of course, on a day like today, we would be moving really slow because our bodies would be cold and our metabolism would be really slow. We would have to crawl out into a sunny spot and warm up before we could function properly.
Luckily, we're not.
So next time we fall asleep in class.
Luckily, most of you aren't reptiles, but in the morning, some of you seem like very cold reptiles.
So if we fall asleep in class, we can be like, oh, I'm sorry,
I'm sorry. Yeah, sorry. I'm honoring my reptilian self, right? All right, so here we go. The sum of the forces equals m or dmv dt. All right. So the difference between these two is whether mass is changing or not.
So the second one is changing.
Yeah, in this case, we're allowing mass to change. All right? Now, in many, many things, we assume that the mass is not changing. We have found out that in nature that this is really a bad assumption, going from here to here. Okay? That mass stays constant. There, in the bigger picture, in the bigger scheme of things, mass is not necessarily constant. One of the views of modern physics is that mass changes with velocity. Okay? So when you get going really fast, your mass changes. And so you can't make this assumption anymore. All right? So this assumption is only good if the mass is approximately staying the same. All right. From here to here, let's change this around. Sum of f dt equals dmv. And let's get rid of that sum. Because what that really means is integral. Okay? And dmv is the change in mv. All right? So most of the times they just write that delta mv. Okay? Okay, what's mv?
Momentum.
Momentum. And so in many books you'll see this written as J equals delta P. That's the simplest version of that equation. Though sometimes not the most practical to look at, because joules equals change in pressure sometimes confuses us, right? All right, that is not joules, that's impulse equals change in momentum. All right, so this is impulse right here. That's impulse. This is the change in momentum right there. All right? So you will see this many multiple ways. So let me write all the ways that you might practically see this. Okay. J equals delta P. Okay, well this side is integral f dt. If the force is remaining constant, a lot of times you'll just see it this way, f delta t. But that's only if the force is staying constant, right? This is the most general form. All right, on the other side of the equation, literally this means change. What does change literally mean? Mathematically.
Result final minus.
Yeah, final minus initial. Okay? Final minus initial. All right, or you might see it this way, delta mv, which literally means mv final minus mv initial. But if the mass stays constant in the problem, then you'll see it as m delta v, or perhaps m v final minus v initial. But this is if the mass is constant. Let me box that. I put it underneath. It looks like I divided it. I'm not trying to divide that. Okay? So this is only if constant mass is correct. Okay? If the mass is changing, you need to be aware that you have to take that into account. All right. So these are all the different ways you'd see this thing written. Any variety of these two sides put together. Okay? And you'll use whichever one is the most convenient for you. Now, let's talk about units for a second. So what units do we have over here? Newtons and seconds. So impulses in unit seconds. Let's look over here. What's this side in? Kilogram meters per second. And those must be the same thing because they're equal. So a Newton is a kilogram meter per second squared times a second. And so we end up with the same thing. Okay? So you can write impulse or momentum with either set of units. It makes no difference. Okay, these are vectors, so please be aware we have vectors going on here. So this is a vector, this is a vector, this is a vector. So the impulse is in what direction?
Direction of the...
Yeah, the direction of whatever the force is, right? Because time is a scalar, so a scalar times a vector just scales up or down the vector, but it maintains the same direction, okay? All right, now over here, this is a little more tricky. This change in momentum is a vector. That's in the direction of the change in momentum. Not the initial momentum, not the final momentum, but the change in momentum. So let's go through this again. If I started with this momentum, momentum 1, and I end up sometime later, time goes by, and I end up with this momentum afterwards. What's the change in momentum?
That way.
Second
Okay, we've done this before, right? If this is the original, and then I have to add something to it, what did I add to it to equal that? Well, this is my resultant vector then, right? So my resultant will be this way. And notice this is where I start, and this is where I end. This is my final vector. So this plus something gives me this one. So what I'm adding to it is this, right? This is my change in momentum. It's that way. Now, yes, go. Is everybody okay with the way I just explained that?
Yes.
Okay, because we've done this before. If that confuses you, just remember this. If this is vector A plus something equals vector B, and this is a vector, remember that A minus B equals that something, right? No. I did it backwards.
B minus A.
B minus A, vector B minus vector A equals that mysterious vector in between, right? And you can do that as well. So which way is B vector? B vector is this way, right here. Which way is minus A vector? Minus A vector is this way. So here's B plus a minus A gives me my resultant, which is my question mark. Notice that my question mark here and this one are the same, right? So either way you want to think about that, you get the same thing. So either think of it as algebra, B minus the final vector minus the initial vector gives you how much it changed, or you can think of it as, well, what do I have to add to the first vector to give me the last vector? Okay, either way, you get the same result. All right? So just be aware, everybody, this is the direction of the change, not the original, not the final. So sometimes there are questions like, okay, you've got an object. Here's a person. Person running this way. They have a mass, they have a velocity, and they're running this way. They run into a brick wall, and then afterwards, they're not even on the ground. How'd that happen? They got really long legs.
No normal.
All right? And then,
Right on.
and they got a pointy right arm. They're carrying a spear.
Cha.
And they hit the wall, and after the wall, they bounce off, going this way, and they still have a mass m, but now they're going a velocity 1/2 v.
What
Okay.
if like they lost an arm or something?
Change of mass.
We'll assume that they've maintained all their body parts and mass is
We're
constant.
going to do
But that's an interesting question. All right. What is the change in momentum?
That would be equals of V.
Wait, it depends how much the wall moves. Or the
Three
time
axes.
is touching
Okay,
Final is
the wall's
negative-
not moving.
Final is negative 1/2
He
MP.
goes to the
Now, I have written 1/2 V.
3/2 MP.
Now, but this is a vector, right? So which way is positive? You want to pick that way as positive?
Yes.
If that way is positive, that's negative.
So it's
So
negative.
change in momentum equals final minus initial. So that's minus m 1/2 V minus a positive mv, which gives me a total of negative 3/2 mv. That's my change in momentum. Now you got to be careful, everybody. Please, please remember this is a vector, and it really helps you if you just think about it and do the math. Final minus initial, final minus initial. Make sure you got your signs on. Because students will do one of two things. They'll either say the answer is 1/2 MV, or they'll say that it's 3/2 MV, which is also wrong because it's negative 3/2 MV. Okay? Because there's a directionality associated with this. This is a vector. Since this is a vector, you got to have the right sign. Okay? So which way is the impulse then? All right, whatever direction this is the same direction as this, right? So the impulse is this way. Now, somebody explain to me why that makes sense.
The wall has a-
Yeah, because if you're going that way, you need a force this way to turn you around, right? Okay, so that it should all make vector sense, okay? And the magnitude of our impulse is this. So, let's say you run into a brick wall, or you run into a spongy pillow wall. Why does one hurt and the other not?
Because the time changes the time.
Yeah, because the deal is brick wall, you stop and turn around quickly, which is not good. Or if you hit pillow wall, you have lots of time to come to stop and turn around, and so the force is much less on you. So you can get the exact same impulse with different forces, with different force time combos, okay? Combinations. All right. All right, so we got this person not paying attention to what they're doing, strolling this way, and we got this person not paying attention to what they're doing.
They have a big head.
I want to say there too, but it's weekend.
Going this direction.
So it's me
All right. So they're moving along, and happy person is walking along and runs into crabby person, which of course makes crabby person more crabby. But how is the force that happy person puts on crabby person, how does that compare to the force of crabby person on happy
They're the
person?
same.
They're the same. Thank you. You have been indoctrinated into the mantra of physics. He's asking this question about two forces. They must be the same. It's exactly right. So the force on crabby person and the force on happy person, they are exactly the same. Now, how long is happy person in contact with crabby person compared to how long crabby person is in contact with happy person?
The same.
Should be.
No. I don't want
Yeah.
to be in contact with the other
It can't be.
person.
I know. It has to be the same.
I'm touching you, but you're not touching me.
Yeah, exactly. Yeah. Stop touching me. I'm not touching you. You're touching me. All right, so the time is the same. Look at that. Time is the same. Oh, no. If time is the same, then what else is the same? Impulse is the same. Are the impulses the same?
Yes.
No.
No, because they're in different directions in the vectors.
Direction.
They're the same magnitude, but opposite directions.
So isn't that the same
So-
forces though? Even though we said they're equal.
Yeah, we said they were equal, the forces.
Okay, sorry. Shh. Forces are equal but opposite direction. All right, now wait a minute. How does the momentum change of crabby person and happy person compare?
Equal enough.
Equal but opposite direction. This person gets a positive change in momentum. This person gets a negative change in momentum.
This person starts out with a positive.
Now, everyone, this is the essence of the coolness of this. If you combine the system, what is the net impulse on the system?
Zero.
Zero. So what's the net change in momentum of the system?
Zero.
So we have conservation of momentum. Okay, and that's the essence of conservation of momentum. Now, here are the rules for conservation of momentum. Rule number 1. You must include all objects that are interacting. Because if you include all objects that are interacting, then they will all have equal and opposite forces on each other. They will all have equal and opposite impulses. They'll all have equal and opposite momentum changes, and so the net momentum change of the system will be 0. So you must include all of the objects interacting. If you cannot include all the objects that are interacting, you cannot do conservation of momentum. Okay? Like if you jump out of a plane and you're running into things on the way down, slamming into birds and such, you and the birds are imparting forces on each other. You can include all those, but the force of gravity is affecting the motion, right? So unless you can include the Earth in the problem as well, then it's not conservation of momentum.
What about the thing where we ran into a wall?
Ah, that was not conservation of momentum. That was the impulse from the wall changed the momentum of the object. Now, that's a good question. So like for instance, when happy person runs into crabby person, okay? These objects are imparting forces on each other. Are there other forces going on?
Yeah.
You bet. What are they?
Gravity.
Okay, you got a gravity, and you got a gravity,
Drag.
and you got a normal, and you got a normal.
Oh,
Friction.
God.
Okay, we'll assume air resistance or drag is small.
Friction.
There could
That's
be.
pretty big.
Flying
Very
squirrel.
wide.
We'll streamline it. He's wearing a streamlined helmet.
Hey Arnold.
All right, there you go.
Like Stewie Allen, the balloon.
Couple him.
Yeah, I know.
All right, the deal is this though. Watch.
Arnold.
These cancel.
Yes.
They cancel each other out. So now friction maybe. Friction between them and the ground, right? Now that might be a legitimate concern in a car crash because you might have tires locked up and skidding, right? Okay, so the deal is this. If there's an outside force, sometimes we neglect it if F delta T, all right, as long as this outside impulse is small enough, like air resistance, that's not going to really do anything, right? In a car crash, the car crash itself, this friction is only going to matter during the car crash, right? So as long as the time of the car crash is small enough, we can still neglect the frictional effect that's going on during the car crash. Because otherwise we'd have to include the Earth in the problem, right?
Let's leave out the Earth.
So what we do is we knowingly neglect friction in a car crash.
Would you have to
Now, if they're colliding like this, head on with the wheels not locked up, then you can easily neglect friction. Okay? Now, if you've got a car coming this way and a car T-boning it, there's going to be friction as these tires start sliding, right? But as long as the car crash time is small enough, it won't make a lot of difference. Okay? It will affect it.
It's an icy road. so
All right? Yeah, so we assume an icy road or something. All right, we had a question somewhere. Somebody
Oh,
had
I
a
kind
question?
of had a question.
Yeah.
Like, is there like physics for like ghosts kind of thing? 'Cause, like on 75, I heard that there was like a lot of accidents because it's like a graveyard within there or whatever.
Ghost electroplasm affecting the
Well, like,
gravity.
if they can like tell like what kind of like if
Ectoplasm.
something could be like logical in the accident, but like it had like outside forces acting on it. That'd be interesting.
The thing about all the pseudoscience stuff,
Pseudoscience.
Fringe.
like,
That's a great show.
the thing is that under further investigation, if it doesn't present a trend, then there's no way to predict it. Now, let me make clear,
Okay.
science does not know everything. As opposed to some scientists who claim that they know everything and are pontificating just like other people are, right? So the thing is that science is a growing body of study, okay, which does not know what the answer is. It just progresses towards what they think the answer is, right? Now, that doesn't mean that just because something has in front of it the theory of something, that doesn't mean that it's wrong. It just means that they're opening up the possibility that it might not be exactly right. Okay? Anyway. So no, we don't have any ghost physics.
Very cool.
Not yet anyway. Maybe someday.
Interactions in the sub-ether.
That's right. That's right. Yeah, it's a different plane of existence, and so we don't know what physics works there. We haven't been there to measure it.
Maybe like in like
All right.
100 years you'll come back and be like, this is how it works.
That's right. That's that baby that's dreaming. We need to have a little
Baby
helmet that you put on a
geniuses.
dreaming baby.
They're
So
talking to ghosts.
they are. Okay, this time scare them this way. All right. Okay. Now, what about the time when the person runs into the wall, like my earlier example? Walking along, runs into the wall, bounces off. Why is that not conservation of momentum? No, because it's dumb is not an adequate explanation.
Because the wall's attached.
Because the wall is not free to move. The wall has an outside force from the ground that keeps it from being able to move, right? So conservation of momentum doesn't work because of an outside force. So it
So
brings me to
really-
rule number 2.
So really, the world moves a little bit when we run into a wall?
You bet. You bet. So like, for instance, if I start running this way, the world starts spinning that way.
We should all run in one direction.
That's what I
Now-
said, but nobody wants to.
You can see that easily, like if you stand on a skateboard and you jump that way, a skateboard goes that way. You jump off of a big skateboard, and you go that way, and the skateboard goes back that way less, right? All right. Now, if you're on a boat, and you jump that way, the boat goes back this way, but you're getting to the point where the boat is more massive than you are, right? Okay, you get on the earth, and you jump that way, the earth goes that way, but the thing is that the mass of the earth is so huge, its recoil is so small, you don't notice it, okay? It's just too tiny. Yeah, Amy.
If the entire world's population had like 5 kids each and we all overpopulated and we all ran in the same direction, would we spin up?
We've actually calculated that before, where we, said if we were all world-class sprinters, and we got all 6 billion of us on the equator,
World-class
and we all
sprinters.
ran, in the direction east, could we slow the Earth down? And the answer is yes, but no. Yes, in theory, no, in practicality, we can't. And the thing is that, think about it, if I start running this way,
You hit
the
the
Earth goes
ocean.
that way,
And you hit
but
the
when I
ocean.
stop, it all goes back, right?
Right, but if we kept doing it.
You can
You're
run
gonna
on
run.
the water.
You're gonna need a lot of support material
They'll make
to
a
feed
bridge
these
across
people
the
as they're running.
Yeah.
We'll all be in shape. So
That's true. It's like the people on the equator are really clocking around, and Santa's doing this. Except he's doing it a lot slower, 24 hours to go one time around, right? But the people on the equator, 24 hours to go all the way around the Earth.
Without gravity, they'd be launched.
Which is what? It's like 330 meters per second. The people on the equator go.
Oh my gosh.
Hey, by the way, that is why if you're going to launch a rocket into space, you launch it close to the equator.
So they go like,
Because you already have it.
Because you already got a nice speed going. Okay?
that's why it's
The
all in
French
southern-
launched theirs from French Guiana, down in South America, which is right on the equator, very close to the equator. And we launch ours from Cape Canaveral, a southern part on the U.S. Now notice they always launch rockets east, and that's not just so that they don't fall on the United States, okay? They launch them east because we rotate east, right?
Oh, so they can like boost the...
So it boosts it. The rockets that the French launch from French Guiana have it's like a 4% advantage over our rockets because they're closer to the equator. That's right, stinking French. And they have a 4% advantage. They can carry 4% more 4% more payload than we do because we're starting at a lower velocity. If we launched from Santa's house, it would take a lot more energy to launch things into
So we
space.
should go steal French Guiana?
That's right. That's right. We should have war on French Guiana. Take their launch pad. Now, right here, conservation of momentum. What's the first rule?
You include everything.
You must include all objects that are interacting. Second rule is, you may not have any net outside forces. No net outside forces. Okay, so running into a wall doesn't work because you can't just include you in the wall, because the wall's attached to the floor, which applies an outside force to the wall. So you have to include the object that's applying the force to the wall, which is the building. But the building is held to the earth, blah, 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 so you got to add the earth to the whole problem, right? So it's not worth it.
But isn't that with
Do it
every
in
single
space.
problem?
No.
Well, we're all
No.
attached to the earth somehow.
When I'm engineering.
But, like two cars colliding. mg, normal force, cancel, cancel. Good, good. Conservation of momentum. All right?
Okay.
All right. Now, conservation of momentum, in this regard, is more powerful than conservation of energy. Because in conservation of energy, you know, you couldn't have any outside forces. Well, you could have a few outside forces, right? You could have conservative outside forces, but no non-conservative forces, right? Okay, also, in conservation of energy, if you had any kind of non-conservative forces at all, it fell apart, right? So conservation of energy disintegrates if you have non-conservative forces, unless you have some way of measuring what that energy turned into, like thermal energy, okay? But here, we can have all kinds of non-conservative forces going on between the objects. Hey, shh. We can have all kinds of non-conservative forces going on between the objects. And as far as momentum goes, we don't care as long as they pair up and cancel out. Okay? That's the cool thing about momentum. Now the bad thing about momentum is it's a vector, which makes the math harder. So you need to be careful because you need to keep track of your directions, and we have a two-dimensional nature of momentum. Okay? So let's solve a couple problems real quick.
Mr. Brennan?
Yes. Yes.
Yeah.
Yes.
Well, like, let's say, like, I'm a big bully, and I grab Raul's head, and I'll slam it into the table.
Oh, okay, wait a minute. Let's get this on tape. You're a big bully. Slam Raul's head into the table. Is that what you said?
Why would you do that to yourself?
Okay, I like this example already. Go ahead. You're welcome.
Well, wouldn't that not be allowed to be the conservation of momentum because I'm involved in it? Because it'd be between the table and then him.
Because the desk has a normal force.
Yeah. Okay, now, the force between you and him, if you push his head this way, then because you're pushing him this way, he'll go this way, but you'll go this way.
Yeah. So what I'm...
Okay, but when he hits the table,
It becomes.
you're including the earth in the problem now, so it ends up being too difficult to mess with in most cases, right? So you'd have to have it as an impulse.
But would it be better for me to beat him up that way rather than me, like, punching him in the face? Because, like, he'd be hitting my hand with the same force.
Yes, if you, okay, let's say, all right, let's use our observations from momentum and impulse, okay,
Help beat up.
to help us know how to hurt someone. Okay, so here we go. Now, a couple of things. Number one is, let's talk about this for a minute, because we need to talk about that anyway. An impulse, all right? F delta T. Okay, wait a minute. What does that mean? No, wait a minute. What does that mean?
Area.
Okay, that means area for this graph, right?
Oh yeah.
Okay, that means area for this graph. Now, remember, you can have two types of variations in impulse. You can have an impulse that takes a long period of time, okay, and has a low maximum force. Or you can have something that takes very little time and have the area be the same, okay? So this is like falling into an airbag. This is like falling and hitting concrete.
Oh, it's so funny.
One is deadly and one is very cushy, okay? The area is the same exact area. Okay, so you want to punch someone and hurt them, okay? So what part of your body do you hit them with?
Naturally, it'd be your elbow.
Okay, yeah, you hit them with a bony part of your body, right? A bony part of your body that will not squish. So an elbow, knuckles, right? Now, you also don't want to damage a vital part of your body, right? So, yeah, the old headbutt in the movies, yeah. Oh, and the bad person or the bad guy falls on the ground and the good guy runs on and headbutts more people. Okay, yeah, exactly. Yeah, right. That is only a good method of trying to injure someone else. Yeah, unless you're okay with injuring yourself, unless you hit them someplace that's softer.
Yeah,
like
if you hit them like on the nose.
you hit them on their nose, then that might be worthwhile, but that's still going to hurt your head.
Hit him in the jugular.
Hit him in the jugular with your head. I want to see that. I want to see the action movie you'd make. There'd be ghosts, and then there'd be somebody headbutt someone's jugular. Oh, you cut off the blood in my brain for a second, but I'm all right. That's gonna leave a nasty bruise.
You know what they say, no brain, no pain.
All right. I can't go on. All right, now these impulses, everybody. Now, if you see one of these graphs like this, first of all, they'll probably either give you a function that you can integrate easily, or they're going to give you a graph so that you're able to actually calculate it in a reasonable amount of time. So like it's probably going to be a triangle like this, or it might be some sort of compound triangle. I've seen some like this before, where it kind of models more of what an impulse looks like. Okay, just break it into pieces, find the area of these little pieces, and add them up. Okay, no big deal. If they give you the function, just integrate the darn thing. Okay, and find out what the force is. The problem is that these functions like this, I don't think they're easy functions to integrate. Okay, so they may, if they give you one of these to integrate, they're probably going to give you something somewhat contrived, like something easy to integrate. Like they give you like maybe like a sine function or half of a sine function or a cosine function or something, so that you can integrate what this area is. Because they have to give you a function that you can reasonably integrate quickly, right? So it's going to have to be something reasonable. What's that?
What would negative impulse be?
All right, now I'm glad you brought that up, because most of the time what they'll say is this is the impulse graph of the two objects interacting. And they give you one graph. And they give you one graph because the impulse of like happy person on angry person is this one. And the impulse of angry person on happy person is this one. The exact same graph, just in negative, right? So what they tend to do is not show you both. They tend to show you just one. And then they're hoping that you understand that that impulse will be the same on both, but one will be positive and one will be negative. Okay, does that make sense? So you find the area, and then you decide whether it's a positive or a negative impulse. Okay? All right. Conservation of momentum. You know what? We have worked many conservation of momentum problems in the past. Let's just work. I'll tell you what. Let's do this. And okay, hang on. Before we work problem 911.
It already sounds ominous.
Yeah, I heard it on the Friday.
All right, before we work problem 911, there's one more thing I want to talk about real quick, and that is the 4 types of collisions. There are 4, count them 4 types of collisions, and they are. By the way, why do we talk about momentum and collisions so much? Why do we talk about them together all the time?
That's why we're doing.
Because when things collide, they are objects interacting. And whenever you have objects interacting and you can keep track of all the objects, it's perfect for conservation of momentum. Because remember, all we have to do is keep track of all the objects that are interacting, and then we can use conservation of momentum as long as there's no net outside force, right? So, collisions. There are 4 types. 4 types of collisions. And they are, number 1, explosion. Number 2, elastic. Number 3,
Partially.
inelastic. 4, sometimes called partially elastic. And then you have completely inelastic. Okay? Now let's draw a picture of each one of these. Completely inelastic looks like this. You have two objects that are moving or not, well, at least one of them's moving before. They may be moving, they could be moving in the same direction or whatever, but when they collide and they hit, and after they hit, they stick. So they go off together. So the key thing is that they stick together. All right? In an inelastic collision and an elastic collision, they bounce. They do not stick together. So bounce and bounce. I like to call this one, though, a perfect bounce. Okay? And I think we know what an explosion is. Now, an explosion can be something sitting still and then exploding, or it could be moving and then separating. Okay? Like a rocket. What was yours again?
Arc, the cannonball we did last.
Yeah, like the cannonball we did last time. The cannonball was moving through the air and then it exploded. Or a rocket that's going up and the stages separate. Okay? So the key thing here is that there is some sort of separation. Okay? There's some sort of separation. Okay, now here's the deal. In all of these, conservation of momentum, the answer is yes. Conservation of momentum works in each one of these. All right? As long as you can keep track of all the objects and there are no net outside forces, bingo, it works. So what is the difference between these?
Energy.
Yeah, the difference is the kinetic energy. How does the kinetic energy compare initial to final? Okay, initial and final. Oops, I'm messing this up. So how are these two connected? All right, the deal is that in an explosion, you end up with more kinetic energy at the end than you started with. So some sort of work was done, or some sort of stored energy was released. So like in an explosion, literally, it's chemical potential energy turning into kinetic. Or like if you are standing there on an ice skating rink with somebody else and you push them that way, they go that way, you go this way. Well, you've done work on each other. Okay? The work does or increases the kinetic energy. So what we end up with is that the kinetic energy final is greater than the kinetic energy initial. Okay, in a perfect bounce, the kinetic energy initial equals the kinetic energy final. Okay? In an imperfect bounce, or an inelastic or partially elastic collision, the kinetic energy final is less than what you started with. You've lost some of your kinetic energy to something. Like either the object deformed, like in a car crash, those are not perfect bounces. That would be crazy if they were perfect bounces. There'd be a lot more death and destruction if collisions were perfect bounces.
Well, but you can pay less for your insurance.
Your car would be okay, because it would not deform, and you'd be bouncing around, but it would be hard for you to come to a stop. All right? And this is also true in a completely inelastic. The key thing here is that this one loses more energy. Okay? This one right here is the most kinetic energy lost that is possible. Okay? The most kinetic energy that's possible to lose and still have conservation momentum is when you hit and stick together. Okay? Now, are there very many perfect perfectly elastic, perfect bounces, kinetic energy before and after the same.
No.
Like atoms.
If the force between the objects is a conservative force, then you will have a perfect bounce. So anytime you see a problem like this, with a spring in between, perfect bounce. Or if you have charged particles flying at each other and bouncing off each other, perfect bounce. Okay? So gravity. So here are all the forces. Gravity, electric force, spring force. Those would be the big three that you see. Magnetic force would also work. That's a conservative force. You probably won't see any others. Okay? So, on the atomic scale, we see perfect bounces all the time. So like gases in this room are flying around, bouncing into things, bouncing off your skull. But the atoms don't have these kind of collisions. First of all, they don't hit and stick to you, otherwise the air would collect on you. Second is that they don't slow down, because what would happen if the air molecules in this room would hit and slow down?
Cold.
It would get cold, and then gravity would take over and pull them all to the floor.
And we'd be really cold.
Yes, it would be a vacuum up here and very cold air on the floor.
We're gonna float trying to breathe.
Since we don't see either of those two things, we make the bold assumption that the collisions are elastic. Okay? Very bold assumption.
They're not exploding, right?
Yeah.
So that's
No, they're not speeding up. And we know they're not speeding up with an explosion because
It's not.
it doesn't get hotter. You just sit in a room with air, it doesn't get warmer. So, it's nice the way energy works and momentum
Mr.
works.
Ruin.
Yes.
Is that how the Ice Age started?
No, that's not how the Ice Age started, young lady. That's right.
Atomic collisions became inelastic. That's what happened.
And then just
Yeah. It would all coalesce into a liquid then, wouldn't it? Because once it cools down and, oh man, it would be a dangerous world.
We can't like so do radical physics, so you don't know.
All right.
Road.
Now, one last thing. This elastic collision is kind of cool. This means that in an elastic collision, and only in an elastic collision, you have conservation of momentum, and you have conservation of kinetic energy. So you have two things that you can do at the same time. Now, if you go through all the math of this, in fact, let's do one real quick. Let's say that we have an object here. Let's say its mass is 2 kilograms, and it's moving at 2 meters per second. No, let's make that higher. Let's make that,
10.
all right, 10. 10 meters per second. And over here we have an object that is 3 kilograms, and it's moving to the right at 2 meters per second. This one collides with this one. All right? And then afterwards they bounce off each other. And, well, they'll continue to move to the right, won't they? Yes. All right. Now, if we set up conservation of momentum, we see that mv plus mv equals mv plus mv, because we have 2 before and 2 after. All right? So that's 2 times 10, or 20, plus 6 equals 2 times v final for the one on the left, plus 3 times v final for the one on the right. So we end up with 26 equaling 2v on the left plus 3v on the right. There we go. It looks great, but we can't solve it because we have too many unknowns. So we could do energy. So let's do that. That means 1/2 mv squared plus 1/2 mv squared equals 1/2 mv squared plus 1/2 mv squared, because we have 2 objects before and after. Now I'm going to get rid of my halves, if you don't mind. I'm going to end up with 200 here plus 12 equals 2vl squared plus 3vr squared.
You can solve each other for each other. I mean,
We can solve each other for each other.
Yes.
We have a system of equations.
Yeah.
We have a system of equations. All right.
We let the
Now,
calculator do it.
solve it for me, please. Go, 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 go.
I never figured out how to do intersections on the graph.
All right. Has there everybody see that this is like a real pain?
Yes.
This is a serious pain because of the square. Because what you can do is you can solve this like I did for VL, and then plug it in here. But then you got to square the dang thing, and it's ugly. That's right. Actually, at this point, you might just want to put an equation for it and graph it and see what its roots are. See when it equals 212. What are the answers?
I got
0.4 and 10.
Which one's 0.4?
Oh, B 0.4?
0.4 and 10?
That's not 40.
I don't think that's right.
I don't think that's right.
I got like 4.47 and like 7.57.
I don't think that's right either.
I think we did this to John.
One of those days.
It's John's
John, what'd you get?
birthday.
4.4 and 8.4.
Yeah, I know. I saw the Facebook
These are my dad's.
I got the 8.4.
You got the 8.4? I think John's correct. How'd you do it? Did you graph it?
But
Actually, if I was doing it, I would get to this point and then I would graph it, see where and I would graph a line of 212 and see where the intersects are. I think that was probably the easiest way to do it. And I believe this is correct. Anyone else confirm that?
Yeah.
Since I just made this problem up, I don't know for sure what the answers are, but this is the only answers that have been listed so far that have the right features of the correct answer.
You can check them. Just plug it in.
You can just plug them back in and see if it works. It should work in both equations. But here's the cool thing, everyone, which is very, very sweet. In a one-dimensional, perfectly elastic collision, where you have conservation of momentum and conservation of kinetic energy, I want you to notice something for me. Could you please calculate for me what's the velocity of approach? 8. What's the velocity of recession?
8.
Magic. All right. Every time you have a one-dimensional perfectly elastic collision, all right, what you will end up with is that the velocity of approach will equal the velocity of recession. Okay? Always. So what that means literally for you is this, that V2 minus V1, or it doesn't matter which order you do it in. I'll do V1 minus V2 equals V2 minus V1. Okay? Always. In a one-dimensional. Now, if it's the two-dimensional problem, I don't think this works. I think you're kind of, yeah.
Just run. On this graph or whatever.
Uh-huh.
Like this is 10 and 2. And then this is
Oh, sweet.
the X and the Y. So it's DL.
Cool. So it shows you the original and the final, and those are the only two spots. Nice. That is crazy. I like that. All right, so everyone here. So really, you need to add another equation to your perfectly elastic. It is V1 minus V2 equals V2 minus V1. Now, everybody, let me explain this. This is the velocity of object 1 minus the velocity of object 2. It doesn't really matter which order you subtract them in. Like in this case, you might want to subtract it V2 minus V1, so you get a positive number here, right? So if you do 2 minus 1 here, then after the collision you'll do 1 minus 2, okay? But this is for before, or initial, and this is for final, okay? So before the collision you subtract the 2, after the collision you subtract the 2 in the opposite order. So velocity of approach equals the velocity of recession. Now, that will take the place of conservation of kinetic energy. So you can neglect that one, and now the problem becomes much, much simpler, because you have a simple conservation of momentum, and then you have a simple one of these. And look what this becomes now. Here's our first equation, and now here's our second equation. For us, we're going to do 10 minus 2. So 1 minus 2, so that's going to be 8 on the left. And then we have v2 minus v1. And so there's our second equation. This one and this one are our two equations. Let's see how much faster it's going to be to solve those two. So that's no squares. Got it? That help? All right. Next time, we will talk about two-dimensional collisions. Are there any two-dimensional problems on your e-homework?
Yes, but it's easy.
Is it easy?
Yes.
All right, guys. All right. Well, let's just talk about it real quick to make sure we got it. All right. Then we'll be through with linear momentum. Okay. For our two-dimensional collisions, the key thing for two-dimensional collisions is that since it's a vector, you have the momentum before in the x, and the momentum before in the y must equal the momentum before and after in the x and y. Okay? So you have this issue. Object coming along collides with this object. This object goes up and bounces off this way. So this object has to go this way. All right? The deal is our original momentum is mv in this direction. Now I'll tell you everyone, this is something that students miss all the time. Most students will get the fact that, well, if it was going this way before, then these two afterwards have to add up so that these cancel, and that this part here, the mv here and the mv here, these two have to add up to be this one. Right? Now the problem is that students think, because they're drawing arrows, they think they're drawing velocity vectors. These are momentum vectors, okay? This must be conservation of momentum, not conservation of velocity, okay? Now if the two objects have the exact same mass, like pool balls, then the masses all cancel and you have conservation of velocity essentially, because the mass cancels out. But that's not what we have in general, okay? So what if I had an object traveling this way? Let's say this has a mass of 100 kilograms, traveling this way at 20 meters per second, collides with this one, traveling this way, and say this is 200 kilograms, traveling at 10 meters per second. All right? When they hit, if they hit and stick together, the deal is that here they are, hit and stuck together. Their momentum afterwards has to equal the momentum they have here. So if this is all x momentum, then before we had x momentum initially of 2,000 Newton seconds. And here we have y momentum initially of 2,000 Newton seconds. So this is going to have 2,000 Newton seconds this way and 2,000 Newton seconds this way for a grand total of 2,000 times the square root of 2 Newton seconds. But that's the momentum, and then you have to divide by the mass to get the velocity of it. Now we know this angle is 45, right? Okay, we know it's going up at 45. We have to divide by the mass. But what's the mass of the object?
300.
Yeah, 300. So if you divide that by 300, then that will be now the velocity, meters per second. Okay? Does that make sense? All right, I think I have one in your review packet, one two-dimensional momentum. And that's off an old Physics B test. They haven't had very many two-dimensional momentum problems on the Physics C exam. So it's kind of one of those things that I'm just waiting for them to put one on sometime. And so this may be the year. So let's make sure that we understand how this works, okay? They always have a multiple choice or two of this, okay? But usually they don't have a free response, but you never know. Yes?
Can you go to the blood thing so I can avoid the rush?
Yes. Run. Give your blood to the vampires.
Cindy, is your going to make it have a meeting size for a Russian?
Yes, go ahead.
Can I go to class?
We all
Can I go to class so I can avoid the rush?
or just make a dinner. Can we all
Can I just
leave?
go home so I can avoid the rush?
I second that motion.
Yes. When do I have tutoring?